I will share my screen directly on the material that was shared to you in Canvas because it has built-in examples. That way we can follow through. At the same time, when you already study, you can directly go back to the recording and listen to it while looking at the PDF copy that was shared to you in Canvas. So allow me to share my screen in Canvas. Okay, so this is the one. I hope you could see it. Can you see it?
Yes,
This is
miss.
the one that I have reviewed to you a while ago, type 1. So dealing with the sine or cosine function, which can either have an odd positive exponent in case 1 and an odd, rather a positive even exponent in case 2. So this afternoon, we will proceed with type 2. So under type 2, we also have two cases. But what is this type 2? So if in case 1, you only have a single function, it's either a sine or either a cosine. So no combination of these two. Now type 2, you already have a combination of the two. So let me enlarge this one that way. Okay. So that way you could see it. In here, this time you already have two functions. You have both the sine and the cosine. So let's look at case 1 first. So I'm sure the cases under this particular type 2 complex trigonometric function would be dependent on the identity of the exponents of the sine and the cosine function that you are seeing here. Okay? Now, either m or n is an odd positive integer. So this m and this n that you see as exponents of the sine and the cosine function respectively can either be positive and odd in nature. The other exponent is any real number. So what does this mean? If your sine is odd and positive, the cosine, or rather if the exponent of the sine is odd and positive, the exponent of the cosine can be any real number. The same goes true if it's the cosine which is raised to an odd positive exponent. The exponent of the sine this time could be any real number. Do you get it? So either of the sine and the cosine can be raised to an exponent which is odd and positive. So either of the two. And it is paired with, so let's say the sine is odd and positive ang exponent. So the cosine can be raised to any real number exponent. The same thing if it's the cosine, which is being raised to an odd positive exponent, the sine could be raised to any real number exponent. So look at the example here that we have underneath. Okay, you have here the sine cube of x and the cosine squared of x. What's being done in here is that the function that has the odd exponent was split into two. Okay, the sine function and the sine squared. So you can see here the sine squared of x and the cosine squared of x, they were put together side by side. The one that was set aside from the sine was written here. If these two, I will annotate, if these two is multiplied, the sine squared here and the sine of x here, you will have the original sine cube of x. Okay? Now, what's the purpose of having to split the sine function in here? The purpose of splitting the sine function in here is that if you have already expressed the sine squared here in terms of the cosine squared function, the sine of x dx, the sine of x dx will represent the derivative of the cosine function. It will represent, I will repeat, the derivative of the cosine function. After, of course, you have converted this sine function, the sine squared of x function that you have into cosine squared of x. Now, why will you do that? That way, you will only have one particular expression in terms of cosine that is related to the sine of x dx, because the sine of x dx is the derivative of your cosine. So if you notice, the sine squared of x here was now written in terms of 1 minus cosine squared x. It's its equivalent identity. So the purpose of that is you can distribute the cosine squared here to these two. That way you will all have cosine functions. So the first part, you will have cosine squared of x multiplied to 1 will be this, times the sine of x dx. The second part, you have cosine squared of x multiplied to cosine squared of x. That would be cosine to the fourth of x. Now multiplied to the sine of x dx. So in these two terms that you see here, class, your u are all cosine of x function. Your du is negative sine of x dx. But since you already have the sine of x dx here, all you need to do is multiply it with negative 1, and before such integral, you also multiply by negative 1. Then what happens to this one? The 2 and the 4 that you are seeing here, it is to be interpreted as the exponent of the cosine function. Then if it is the exponent of your cosine function, you will resort to power rule. Why will you resort to power rule? Because this is just like u raised to n du. U raised to n du. So it's just power rule. Because the derivative of your u is the sine of x dx, which you only need to multiply by negative 1. So true to what I was saying, class, you could see that you place here negative, so you place here negative outside. You place here negative here, negative 1, to complete the du. So if you use power rule for the cosine squared, it would be cosine cube of x over 3. And then, of course, affix the negative sign. For your second term, you already have the negative 1 in here, so there's no need for you to multiply this one by negative 1. Just transfer this one in here. That way, the du of the cosine here is complete. So you just need to perform power rule to cosine of x raised to 4. So that would be cosine of x raised to 5 over 5. Now it's positive. Why? Because this negative you already transferred inside. Okay, so in here, you use power rule. Power rule by making sure that the functions that you have here are made into one particular trigonometric expression with the function that was set aside as its derivative. Do you follow? Do you have questions before I proceed to the second example? Okay? So wala question. Everybody understands. Now, Joshua, okay. Is it okay? Go ahead. What's the question?
Miss, question. So for the final answer, Miss, there are no sine x dx anymore, Miss. So where did the sine go, Miss?
Okay, let me use a different font. The purpose of the sine of x dx, as I was explaining a while ago, is it will be the derivative of the cosine. Because if you use the u integral of u raised to n du formula for this cosine squared of x and this cosine to the fourth of x, the du of the u should be there. So I have written here, if your u is cosine, the du is negative sine x dx. So this one stands as the derivative of your u. You cannot use power rule unless the derivative of the base here, which is u, is present. Do you get it? So that is why it's not participating in the power rule here in the trigonometric function cosine, which you use the power rule because it's the derivative of the u. This is how you should interpret power rule. you can have the answer here u raised to n plus 1 over n plus 1 provided that derivative of this u should be here. Now, your u here is cosine. So, its derivative is negative sine of x dx. So, that's the purpose that you have negative here outside because you completed the sine of x dx here by multiplying it by negative 1. So that you will not alter your original integral, you will have to place negative 1 outside. Do you understand now?
Yes, miss. Thank you.
Okay. Now I will proceed to the sample 2 if there are no questions here. Okay, no more questions. Sige. Now we go to sample 2. Now this is an example wherein a function is raised to a positive odd exponent. This is positive. This 3, let me annotate. This 3 is positive and odd. And the other one is raised to any real number exponent. Your sine function here is raised to an exponent which is 1/2 because it's under the radical sign. So what you do here in here is exactly the same as what we did with sample 1. You split this function which has the odd positive exponent into one function raised to exponent 1 and the other being even now. So you can see it was split here to cosine squared of x and the cosine of x dx. Now, what's the purpose here? The one that you set aside, the cosine of x dx will again represent the derivative of the functions that you have here after you have made these two functions similar. What do I mean with similar? Since you have here the square root of sine x, you need to convert the cosine squared of x in terms of sine x. That way, they can both have the derivative of the sine x, which is cosine of x dx. Now, true to what I have said, I will change the font here. You see this cosine squared of x here? Hindi pagtandugon because this one is the derivative of the sine. The cosine squared of x here will be converted using this identity. The 1 minus sine squared of x. Now, aren't they all now homogeneous in terms of the function? When I speak of homogeneous, pareho na sila. So, since they are already the same, you can now do multiplication. So you distribute the square root of sine x as a multiplier to these two in here. If you do that, the first one, the square root of sine x times 1 is just simply the square root of x. And of course, it will be multiplied to this cosine of x dx here. The sine squared of x, when multiplied to the square root of sine x using the rules of exponent in your algebra, will require that you add the 2 as an exponent here to 1/2. So 2 and 1/2 will be 5/2. See this? The sine of x raised to 5/2 because you already combined these two. And again, you get to see that what's happening here? Cannot change the color. You can see here that you have the cosine of x function, cosine of x dx function here. Your cosine of x dx is actually the du of your u, which is sine of x. Sine of x is your u. Your n, if you will use power rule, for the first term is 1/2. For the second term, it's 5/2. The derivative of the u is sine of x. So now the du is cosine of x dx. So just like sample number 1, the cosine of x dx will not undergo power rule. It's the derivative of the u. So what will undergo power rule is your sine function. So if this will undergo power rule, 1/2 plus 1 is 1.5 or 3/2. So this is sine of 3/2 x over 3/2. So it could be written as 2/3 already in here. Now, if you do power rule for the sine of x raised to 5/2, that would be plus 1. So 5/2 plus 1, that would be 7/2. Divided by 7/2, or you see it now here as 2 over 7. So in both cases, the tool that you use is power rule. You use power rule in evaluating the two integrals here. That is after. That is after you did already trigonometric transformation. Do you have any questions? No more questions? So remember before I go to the case 2, this is just case 1. In case 1, you have either m or n is a positive odd integer. The other one is any real number. So we are talking about the exponents m and n. So either. Case 1 says here either. Either. What about case 2? Case 2 is different. So if you look at case 2, says both. Not either, but both m and n are even positive integers. So even. So this is quite similar, right, to type 1, case 2. Type 1, case 2 is when your sine function or your cosine function is raised to a positive even integer. This one, since you have both the sine and the cosine in type 2, both of this m and n exponents of the sine and cosine are even. Where in the case 1, either is odd. Okay, in here both are even. So what will you do? Just like in case 2, type 1. Case 2, type 1, you will use this same identities. The double angle cosine equivalent of the functions that were raised to a positive even exponent. Okay? So both you will convert to this one. 1 minus cosine of 2x over 2 if it's a sine squared of x, and 1 plus cosine of 2x over 2 if it's a cosine squared of x. So the same identity to use as case 2 type 1. Okay, just give me a minute, class. Now, let's look into the examples that we have under case 2. You can see here, both are raised to 2. Both are positive, even exponents. So both were converted into the double angle cosine identity. So you have here for the cosine, this one is for the sine squared, and this one is for the cosine. Okay? When you have this multiplied, of course, the denominator is 4. And this is 1 minus cosine squared of 2x. If you look very closely, this one is another case of a positive even exponent. So meaning you will again convert this using the double angle cosine here. So what happens is this 1/4 that you have will be integrated 1/4 dx. Whereas this one will be converted again using this identity. So since you already have 1/4 here, class, you place here negative 1/4 and then convert this into this equivalent identity. Your angle is 2x, you will need to double it, that will make it 4x. So cosine squared x is 1 plus cosine of 2x over 2. So you change the 2x to 4x and you will have plus sign here. And you will have another 2 here in the denominator. So it follows, class, that this 1/4, if multiplied to this 1/2, will be 1/8 x. This is minus, so you have here 1/4 x minus 1/8 x if you're going to integrate this 1/8 dx. This one, on the other hand, for this term, you will have 1/8 cosine of 4x. You can see this? 1/8, 1/4 times 1/2, 1/8 cosine of 4x. You may wonder why, where did this other 1/4 came from? You see this one, the 4 that was introduced in the dx? It's because if you will integrate a cosine of u du, this is to be interpreted that you can answer here sine of u for this one if and only if the derivative or the argument of your cosine, which is u, is complete. So if your u in this case, in the cosine, your u is 4x, the du of that is 4dx. So the reason why you have this 4 is because of this. The derivative of 4x is 4dx. You introduce 4 here, there's a need for you to multiply your integral before it by 1/4. That way you did not alter the original given integral. So in this particular third term now, you will have 1/8 times 1/4, and that would be 1/32. And you will have the sine of 4x. The 1/4 x minus 1/8 x here actually could be simplified further by writing 1/4 minus 1/8 is 1/8 x minus 1/32 sine of 4x plus c. So that's the simplified final answer for our example for type 2, case 2. Do you follow, class? I will wait if you have questions. Do you have any questions? There is none, so it's clear. Okay, so I will clear my markings here and we'll proceed with type 3. Okay, we have, by the way, 6 types here under trigonometric transformation. Now, in type 3, so the first 2 types deals with the sine and the cosine function and a combination of such. Type 3 deals with the tangent function or the cotangent function. Okay, m here, the exponent of this tangent or cotangent function has to be a positive integer. So it's not limited to a positive odd integer. It's not limited to a positive even integer. The only requirement is that m should be a positive integer, meaning a positive whole number. M cannot be negative under type 3. Okay, now let's look into this one based on the examples. Let me check last if I can widen this. Okay, now in the first example, you have the cotangent of x raised to 4. So it's positive, so it's okay. It was split to 2. You have cotangent squared and another cotangent squared. If you're going to multiply the 2, you will have cotangent to the 4th of x. Now, since the cotangent function, class, has its derivative as the cosecant squared, there's a need for you to convert the second cotangent squared here, this one, into the equivalent identity, which is cosecant squared x minus 1. Okay? We have this identity that cotangent squared x plus 1 is equal to cosecant squared x. Now, we use that identity in here. The very purpose is that we can make the cosecant squared By the way, class, there's no x here, huh? There's a typo here. Or let me just change this one. 2 lang na siya. Cosecant of x squared minus 1. Okay? Now, the purpose of this, and you should have here, by the way, cotangent of x squared. So you should have an x angle here, and this cotangent squared of x should be this one. Okay? Now, the purpose is the cosecant squared of x will be the derivative of the cotangent of x in here. Now, I'll write what should it be here. If you're going to distribute the cosecant, or rather the cotangent of x squared to cosecant squared x minus 1, this will be the two terms that you will be yielding. The cotangent squared x, cosecant squared x, the first here, and the cotangent squared x, which is this one. Okay, it's just cotangent squared x minus 1. So it's just still cotangent squared x. You have this. Now for this one, class, this can already be evaluated using power rule for this one. Your u is cotangent of x. Your n is equal to 2. Your du is negative cosecant squared of x dx. So the only thing that you need here is the negative sign. So you multiply this by negative 1, you place a negative 1 outside. Okay? This particular term can be evaluated now using power rule. However, for this one, the second term, the cotangent squared of x, in here, this one multiplied to 1, this one cannot yet be integrated. So what you do, you again use the equivalent identity. Use the equivalent identity of the cotangent squared x in terms of the cosecant squared x minus 1. So this particular integral was written in this form again. That way, this time, you will have now to integrate cosecant squared x and 1. So if you integrate negative, you see this negative here, negative cosecant squared x dx, that would be cotangent x. The answer is cotangent x. If you integrate the negative of negative dx, that would be positive x. Integrating a dx would be x. Negative and negative, that makes it positive. If you use power rule for the cotangent squared of x here, that makes it cotangent cube x divided by 3. The reason why you have the negative sign here, it's because you need to introduce negative 1 here in the cosecant squared x dx to complete the derivative of cotangent x. So in here, what you made use are the identities, the equivalent identities of the tangent squared and the cotangent squared. So what is written here, class, is only the tangent squared x identity. You can add to this the cotangent squared x, which is cosecant squared x minus 1. These are the identities that you can use depending on what particular function is given to you. Okay? So that the procedure in transforming a tangent or cotangent function raised to a positive, integer is that you split it. You split it into one function that has the even exponent and convert it to an equivalent identity, and the rest could be already integrated. Just in the case in here for number 1. Do you have any questions? Do you have anything to clarify regarding sample 1? Okay, one here in the chat box. Miss, good afternoon. Sorry. It's okay. In my class before, I was also disconnected 3 times because of, I don't know what's wrong with the fiber of PLDT now. Sige. Any question here? Are you sure you can follow? So type 2 is only one function, either tangent or cotangent raised to a positive exponent. Now you will be transforming using a different identity, and the identity can either be the tangent squared x in terms of secant squared x minus 1 or cotangent squared x in terms of cosecant squared x minus 1. Clear? No problem with this example? Okay, since there's no question, I will proceed. Now, I'll go to still the sample, the second sample on type 3. You have the tangent cube of x dx. Positive. However, add. So it's okay. Split it. So you have here the tangent of x and the tangent squared of x dx. What do you do with the function that is raised to the even exponent? Convert it to its identity. So the case of tangent squared x is secant squared x minus 1. After that, you distribute. Your first term will then be tangent of x, secant squared x dx. Your second term will be tangent x dx only. For this term class, you will use again u raised to n. Integral of u raised to n du. Your u is the tangent of x. Your n is 1. Your du is secant squared of x dx. So you see it's in here already. The secant squared of x dx stands as the derivative of your u, which is the tangent of x. So you just use power rule for that. So you have tangent squared x divided by 2. Now, what happens to this integral of the tangent of x dx? If you can recall, when we discussed in Module 1, simple trigonometric integrals, this tangent function, I'll write in here, is equivalent to the sine of x dx over cosine of x. The tangent now written in terms of the sine x and cosine x. Now, if this cosine in the denominator is your u, the derivative of that cosine is negative sine x dx. So you see the only lacking constant here is negative 1. So you place negative 1 outside. Now this is then in the form of du over u. So this will yield what? Under technique, trigonometric, under technique number 1, techniques of integration, this will yield the natural logarithmic function, the ln of u. In our case, our u is cosine. So you see this? Minus, so this sinus followed, minus, so you have the sine, minus the ln of cosine of x. So minus minus becomes plus ln of cosine of x plus c. Do you get it? Note that your tangent of x, secant squared of x, this one is secant tangent or secant x dx. Secant tangent, secant x tangent x, secant x dx. If I'll use a different color, so you will see a different way of solving. This is a different one. Okay, not that one, it will not be seen. If your u here, if your u is the secant of x, this entire thing here will be your du. Du is secant x tangent x dx. That's the derivative of the secant. So meaning, for this one, you can have power rule applied to the second function. So you have secant squared of x divided by 2 plus c. Since if that is the case, you can have the tangent of x cubed dx equal to the second squared of x divided by 2 plus ln cosine x plus c. So in this case, plus, you have two possible answers. If you treat your tangent cube x in this manner, tangent of x second squared of x dx, in this manner, you will have second squared of x divided by 2. So your answer for this tangent cube of x could either be this one or this one. Do you get it? Sometimes when you are that quiet, there are just two things that comes into my mind. It's either you understand fully or you don't understand anything at all. So do you have any questions?
Miss, may
Yes.
question ako, Miss.
Yes.
Paano siya, Miss, na 6 squared x over 2 siya, Miss? So, bali,
Ang
asan,
ini, katuwa, ang ini.
Miss, paano siya, Miss,
Oh,
na-convert?
sige, sige. Erase ko tanan para clear. We're talking about this. Okay? Where is this coming from? In here. Okay? Your tangent x multiplied to second squared of x after you have done this splitting of the tangent function. I hope you can follow through in here. Now that this one can be written in this form. The second of x is split into second x here and another second x. The tangent function is in between. Okay? They're still the same, right? Now, why do we have this one? If in this particular scenario, I'll write second of x and I'll place a dot, second of x, tangent of x dx. Your second of x could be your u. The du of that second of x would be this entire thing. Because the derivative of the second is second tangent. In your n here is equal to 1. Because this is understood to be raised to 1. So that's the reason why you simply applied power rule to the second of x here using the tangent of x second x dx as its derivative. So it's now second squared of x over 2. Do you get it?
Yes, Miss. Thank you.
Sige. Now, any questions? Some more questions? I really appreciate it if you ask questions. No matter how you think it would be trivial. What I mean is, I will not ask the question. Probably Miss Ali will just think that it's simple. Why should I ask it? It defeats the purpose of learning if you don't ask anything, if you cannot follow through. This is probably now, probably for some, easy to follow because you're given it piece by piece, like type 1, type 2, type 3. Can you imagine if everything is given to you and you are not told that it's going to use trigonometric transformation, that it's going to use simple substitution, or that's simply going to use power rule? It would really test you in terms of your critical thinking skills. That is why I really allot time here to ask, do you follow or can you understand? I appreciate those who ask questions because that tells me that they are with me when I discuss. But if you don't have questions because you understand, I'm happy. But let me see if I give you a quiz if I will still be happy, knowing that all of this will be given to you all at once, and you will not be told that this particular integral is type 3. This particular integral is type 1. that would be a different story. Why? Because you will be now the one who's going to apply the principles that I'm teaching you here. So again, do you have any questions? Okay, so there's none. So I'm happy that you can follow through what I am discussing. So I will proceed. Now we go to type 4. Type 3, either tangent or cotangent raised to a positive exponent. It's not important whether it's odd or even. The only requirement is that it should be positive. And you are given the third set of identities here. That co-equivalent identity of the tangent in terms of secant, and that of the cotangent squared in terms of cosecant squared. So I'm referring to tangent squared a while ago. Okay? Now, type 4 is just like type 2. Now, this time, we're not talking about just one function, but two functions. So, what is being paired here is the tangent and the secant. And the other scenario would be the cotangent being paired with the cosecant. If you notice, the tangent will have the derivative secant, and the cotangent will have the derivative cosecant. Now, there are two cases for this, and let's look into each cases one by one. Okay? Now, case 1. The m is odd and positive, and n is any real number. M is odd and positive, and n is any real number. So meaning this m here, which is the exponent of the tangent or the exponent of the cotangent, is odd, positive. The secant and the cosecant, on the other hand, under this case, is any real number. So when we speak of any real number could be positive, could be negative, could be a fraction. It's any real number. Now, what do we do? Okay, split. So you split the tangent of mx secant nx into tangent of m minus 1x and secant n minus 1x and tangent secant tangent x secant x. Again, split the tangent of m x and secant nx into tangent of m minus 1x and secant n minus 1x and the tangent x secant x. So meaning, class, you will subtract 1 from each of the exponents of the tangent and the secant, and that tangent function and secant function which you took from it because you subtracted 1 from their exponents should be set aside. You will follow the same with the cotangent and the cosecant. You need also to subtract 1 from the exponent of the cotangent and the cosecant, and that cotangent and cosecant which you took from each of these you set aside, just like what was discussed here in the tangent x secant x function. What do you do? Set aside the latter. When we speak the latter, this one. And use the substitution secant squared x minus 1 for the former. What does this mean? Your tangent here, you convert to its equivalent identity secant squared x minus 1. If you're given a cotangent function, here in the cotangent m, convert it into the cosecant squared x minus 1. So this is the former, the tangent. The secant and the cosecant that goes with the tangent and the cotangent respectively, if you're given this type of integral here, the second one, will be converted all into an expression containing only secant or cosecant. Why? Because in here you could see that the tangent is to be converted to secant squared x minus 1. It follows that the cotangent here will be converted also to cosecant squared x minus 1. Okay? It would be better understood if we'll go to examples. So we'll go to the examples here. Okay, so we have the examples. Tangent cube x secant to the fifth x. What was the procedure? Take one from each of the exponents, and that was done here. And just place this on top. Okay, you take one from each of the tangent and the secant. So you see, this is now 2, and this is now 4. The one that you took from the tangent and the second was set aside. So this will be set aside. Meaning, class, it will not participate in the process of integration because, as you could see from now, its purpose will be for the derivative of the u, whatever is that u. Now, if you recall a while ago, it says that your tangent will be converted using this identity, secant squared x minus 1. It's done here. Okay, secant squared x minus 1 for the tangent squared x. What happened to the second to the fourth x? Nothing. It's just there. And you again set aside the secant x tangent x dx here. Now, next step is this thing that you did not touch at all. You did not convert using an identity. You will distribute why can't I change? You will distribute here as a multiplier. So this second to the fourth will be distributed to the secant squared x and to this one here. What happens? This second to the fourth times secant squared x will be secant raised to 6x. Again, you see this one? It's just there. It was the set aside derivative. What about this second to the fourth of x times negative 1? You see here negative second to the fourth x. Again, you see the second tangent here. I think majority probably already knows what's next. In this 2 integral that you will process, your u is secant of x. Your du is secant x tangent x dx. So the purpose of this is to be the derivative of your u. You use power rule to the second function. So second to the 7th of x divided by 7 and second to the 5th of x divided by 5. It's negative plus c. Do you get it? So take away one tangent and one second. That will represent the derivative of the second function after you have already transformed your tangent function to its equivalent identity, which is the secant squared of x minus 1. Do you follow, class? Okay, we go to the second example if there aren't any questions. Here you have tangent cube x square root of secant x dx. Now you will be worried now. Why do we have here a square root of x and one is tangent cube of x? What do we do? So what do we do in this case? The same procedure, class, as in the same. Now, what is done here? You take one from the tangent cube. This is the tangent here. So what remains here is the tangent squared. Okay? Now, for the second function, you may think, how am I going to get one from it where in the first place its exponent is just 1/2? Easy. You do manipulation. You really need to have the tangent second function together because it will represent the derivative of the second. So you have it here. Okay, I will annotate. So you have it here. Okay? Since you completed the tangent x secant x dx, which will stand as the derivative of your second with no second function here where you can subtract it, would it be okay that you multiply this original integral by secant x over secant x? Because anyway, that secant x over secant x is just 1. So since you place here secant x, then you place here 1 over secant x together with the square root of your secant x here. So secant x was not written. This expression class is the same as this. It was just manipulated. That way, you will have the derivative of the secant complete. Complete in the sense that it should be the tangent of x, secant of x dx. Now, what happens after that? Change the color. It cannot be seen. So after that, this really stands as your derivative. So you convert your tangent squared of x into secant squared of x minus 1. This one is now this. Okay? What about this secant square root, secant of x under the square root sign? So it's secant of x raised to 1/2 over secant of x. It's here. It's secant of x raised to negative 1/2. 1/2 minus 1 as exponent will yield negative 1/2. Okay? And this tangent x secant x dx, it's still here. You did not do anything to it. You will not alter it because you need it as the derivative. Now this secant of x raised to negative 1/2 will be distributed again, just like in sample 1, to the tangents to the secant squared of x minus 1. If you do that, secant squared of x times secant of x raised to negative 1/2 will be secant of x raised to 3/2. Okay? 2 minus 1/2 is 1.5 or 3/2. This one will be secant of x raised to negative 1/2. So this is your second integral. The secant x tangent x are just your ever-present derivative for the second here. Okay, it's just distributed as well in here. So you use power rule for 3/2. Or the exponent 3/2. So that makes it 5/2 over 5/2, which makes it 2/5. Your negative 1/2 plus 1 is 1/2 over 1/2, which makes it 2. Let's see. Do you get it? Do you follow? Have any questions? So the procedure is to be followed. Take one tangent, take one secant, pair them together with the dx. Set it aside. Don't do anything on it. What you need to transform further is the tangent to the second function. That way, your second function now will be processed using power rule together with that set aside derivative of it, which is tangent x secant of x. Do you have any questions? There aren't any questions? Okay, I will clear my markings here. We'll go to case 2. Okay, case 1, before I go to case 2, is again saying that m is odd and n is any real number. Any real number for n. What about case 2? N is not any real number this time, but n is an even positive integer. M is any real number. Case 2 is the exact opposite of case 1. We interchange scenario. This time, your m will be any real number and your n will be an even positive number. However, in here, in the first one, m is an odd positive integer. In here, n is any positive even integer. Okay? Your m is any real number, but n is not a positive odd integer, but rather a positive even integer. What do you do if this is the case? Right? You split mx into secant squared x secant m minus 2x, and use the substitution for the secant squared of x, which is equal to tangent squared x plus 1. The identity that is used here is the equivalent identity also that is being used in case 1. However, in case 1, tangent is being converted to secant, or it could be cotangent being converted to cosecant squared. In here, it's the other way around. It's secant squared x which is being converted to the tangent of x squared. Or it could be the cosecant squared of x being converted to the tangent squared of x. We are using the same identity. It's just a matter of transposing one term to the other side of the equation. Okay? Now, split. So this is the first time in all the types that we have discussed that we subtract not 1 from a particular exponent of a function, but we subtract 2. In this case, from your second function, or it could be also the cosecant function if you have a cotangent cosecant pair of function, this secant squared x, the remaining second function stands as it is. Then that secant squared x or that cosecant squared x will be converted to its equivalent in tangent squared x or cotangent squared x. Okay? Now, let's look at this example. Cotangent. So, if you notice, samples here are all tangent. So, what if we'll use cotangent cosecant here? Cotangent 2x raised to 4, cosecant 2x raised to 4 dx. So, the instruction is your cosecant, this one is secant. So, meaning you are to touch the cosecant. The cosecant should be split. You take away cosecant squared from it, the other will be kept as is. So, you have this one now. From your cotangent to the fourth of 2x, you have cosecant squared 2x and cosecant squared 2x taken from the cosecant 2x raised to 4. So that's the 2 that you have there. Okay? As suggested here, this one, the one that has the even positive exponent will be converted using this identity. So you convert the cosecant squared 2x here, only 1, to cotangent squared 2x plus 1. Just like this one. So this could be cosecant squared x equal to cotangent squared x plus 1. That's what is being done. The purpose class is very clear that you can combine now all the cotangent. The cosecant squared 2x, which was taken from here, which is not touched at all, will be now the derivative of your cotangent. Once expanded already, di siya pagtandugon kay derivative na siya sa cotangent. So if you will distribute this one as a multiplier, you will have now cotangent. This is cotangent 2x raised to 4 times cotangent 2x raised to 2. This should be cotangent 2x raised to 6. Here it is. It's written here in the second part. And this is the derivative. Okay? I'll underline the derivative. Notice, class, that this time you have introduced already 2 in the dx. Why is that? If your u, I'll write here, if your u is cotangent of 2x, using chain rule in differentiation, the du should be negative cosecant squared 2x 2 dx, the derivative of the theta. So the 2 was introduced here. Rightly so, you should have 1/2 outside. Okay, you place here 1/2. And since the derivative of the cotangent is negative, you should place negative sign in here. So where is that? It's now negative here. You can see that one, negative. And you have 1/2. The cotangent of 2x raised to 6 now uses power rule. So you have cotangent of 2x raised to 7. This should be class divided by 7. So there's a typo here. There should be a 7 in here. So you should have negative 1/2 or negative 1/14 now cotangent of 2x raised to 7. Now, I'm discussing this part here, which you multiplied and processed in the integration because it's written here in the second term already. For this one, you have cotangent to the 4 2x plus 1, it's in here. And you have cosecant squared of 2x in here. So you also completed that derivative. Notice that there was also the introduction of the 2 in here, and you have here the 1. So this should also become negative because the derivative of the cotangent is cosecant. So you see this one, it's negative cotangent of 2x raised to 5. After you use power rule in here, this should be divided by 5. So this 2, this should not be in here. But this should be 10 already. It should be 1/2, and that should be 1/5 for the power rule applied to the cotangent 2x raised to 4. So in this part class, this part, it's right, but it was typewritten here. There was a typo when it's typewritten again in here. This is right, 1/2 times negative 1/5. It should be like that. So your answer should be, the final answer should be negative 1/10 cotangent to the 5th 2x. For this one, it's negative 1/2 times 7. That would be 14 cotangent of 2x raised to 7 plus c. So there's a typo error here and in here. Do you follow? Do you have any questions? Don't have any questions? Do you get the explanation for case 2, how it's different from case 1? No question? You're so silent. Any question? Sige. So since there aren't, yes? Yes?
Wala, miss. None, miss. None.
None? Sige. Probably there's already information overload. Okay. So on Tuesday next week, we will finish type 5 and 6. I will allot the remaining time for you to process your problem sets on all your problem sets, the remaining problem sets that you need to process on Tuesday, and prepare for your third quiz on Thursday. Okay, let me check in Canvas what would be our scheduled quiz. Just give me a few minutes. I'll stop sharing.